Good morning, welcome to this case study webinar, Creating the Digital Office of the Future, hosted by Rockflow Dynamics in partnership with OMV and Cegal. My name is Joanne, I'm part of the RFD team based in Aberdeen. I'm joined by three special guests for this webinar, Cegal and Wolfram from OMV in Vienna, and Marty from Cegal in Stavanger. Before I share some more information about today's presenters, just a few things to mention. All attendees have been automatically muted, so if you would like to ask any of our presenters a question, please pop this into the chat box on your screen, and we'll answer as many as we can at the end. If we don't have time to address your question live, we will follow up with you via email. The webinar is also being recorded, and I'll upload that to the Rockflow Dynamics YouTube channel later today, so keep an eye on our LinkedIn page for updates. And if you have any follow-up questions, please reach out to asktnab@rfdyn.com and we'll be happy to direct your question to the right person. As I mentioned, you will hear from three speakers during today's webinar. The first part of the presentation will be delivered by Gisela Vanegas, Senior Reservoir Engineer at OMV. Gisela will provide an overview of OMV's operations and outline how they were able to overcome bottlenecks in stochastic modelling workflows using solutions from Rockflow Dynamics and Cegal. Our second presenter is Wolfram Questions, Senior IT Project Manager in the Digital Excellence Division at OMV. Wolfram will outline the business's ever-growing requirement for additional computing power and explain the HPC and software solutions that they have devised to address speed limitations. And the final part of the webinar will be delivered by Marty Questions, Product Manager for Geocloud HPC on Azure at Cegal. Marty will provide an overview of Cegal's Geocloud Model and share the benefits of using this particular solution. Before we begin, Rockflow Dynamics would like to thank OMV and Cegal for their participation in this webinar, and of course thank you to all the attendees who have joined us today. I'll now hand over to Gisela to kick off the presentation. Hopefully everyone enjoys the webinar and we look forward to hearing your questions at the end.
Joanna?
Yep, all good.
Perfect. Good morning, everybody. My name is Gisela Vanegas. I'm a Senior Reservoir Engineer working in the New Technologies Department in OMV. And today I'm going to present how cloud computing power has enabled our stochastic modeling workflows. For those of you who don't know OMV, we produce and market oil and gas, innovative energy, and high-end petrochemical solutions in a responsible way. We produced in upstream around or nearly 500,000 BOE per day, coming from Central Eastern Europe, Middle East and Africa, the North Sea, Russia, and Asia Pacific. We are here today to talk about our stochastic modeling workflows, but the first thing to know is why we do this. And the answer is because we need to manage uncertainties. And a good example of this happens every day before leaving the house, when we have to decide if we want to take a raincoat with us, an umbrella, or if it's a good day to ride our bike. And to answer this question, normally, instead of using just our gut feeling, what we do is we take our mobile and we check our weather forecast. And if the weather forecast says there is a 90% chance of rain, most likely we are taking the raincoat with us. And to come out with this percentage, our weather app, they are actually scientists who take images, for example, from satellites and measurements like the air temperature, to build numerical models. And we do this because when we don't know, cannot know, or could have known, only a robust model of uncertainty can help us to make a better decision. In the New Technologies Department in OMV, we go through exactly the same process when we ask ourselves how to pre-develop a field. We take also images in the industry, like the well logs or seismic. We take measurements from our wells, our production data, pressure data, and we generate or create numerical models with the input from subsurface and surface disciplines. And we do all this to get a probabilistic answer. And in this example, if I say I'm finding that there is a 90% probability of economic success with polymer injection, this is for sure the outcome of our recommendation. So knowing why we do it, now let's talk about how we do it in OMV. Right now, we have established two different workflows. The one on top, we call differential evolution. It starts with the geoscientist collecting or listing all possible geological concepts from the structural side and from the sedimentological side. Which development environments are possible, what are the phase probabilities, and so on. And he combines, or she combines, all this into thousands of realizations that are then taken into a clustering process. And we are doing this using streamlined simulation. We do a general sensitivity analysis on our static uncertainties, select the centroids for the clusters, and come out with hundreds of realizations that then we combine with our dynamic parameters, the prior distribution of the dynamic uncertainties, and we take this into history matching using differential evolution. We generate our output, probabilistic outputs, and we use these models for forecasting our development concepts, economics, and finally we feed in Codec, which is our in-house decision analysis tool. At the bottom, we can see our new machine learning workflow. We start exactly the same, addressing all the possibilities for the geological model, but we go straight ahead and combine it with the dynamic uncertainties and go into simulation. And then we generate thousands of simulation runs that we take into a machine learning process. And here what we do is we train from the data and we come out with new geo model with new dynamic parameters that can predict better our reservoir performance. And then we take this into, again, probabilistic forecast to feed in our decision tree in Codec, where we do the decision analysis. So what were the pains before going into cloud computing? We had a fixed cluster and licensing solution that was limited to a bit less of 20 nodes, and it consisted of 16 core machines. Therefore, the experiments were defined, were designed small to accommodate to these resources. Our grids were limited in the cell size to 20 by 20 due to the computational requirements. If we go lower than this, and in peak times, this proved to be insufficient. We couldn't optimize the throughput before, as we only had 16 core machines, and the number of nodes was also fixed, and we were limited to our differential evolution workflow. So basically, we lacked flexibility. What we have right now is a combination of 3 environments. We still have our workstations. We have a local Geocloud, and we have the Microsoft Azure cloud. Why do we still have our workstations? Here we run Codec, but we also have our decision analysis. We also have our data science tools. And in the new technologies department, as we are looking for everything new and addressing everything new, we always need to access to the latest Python or R version, or to any new library going around. And this is why our workstation is still very useful for us. It's just for testing purposes. Then in the Geocloud is mostly where our geoscientists are working. We have there all tools available. In our case, for the workflow, we have the TradeGNAV Studio SL. And then in Microsoft Azure is mostly where the reservoir engineer now is working on only on the simulation side. So how do our workflows look like in these 3 environments? We start first with codec, and here first we design our concept tree, and these are the possible decisions that we can take, or the different development concepts we want to address. And we also generate our parameter table, which is nothing else but the combination of the geological and the dynamic uncertainties that we want to incorporate in the study, or that we want to assess in the study. The first part of the workflow is conducted in the Geocloud, or the local cloud. And first, the geoscientists, as I said, generate the thousands of geomodels. At the same time, the reservoir engineer is working on creating the base case for simulation. And then we go into clustering. We generate our hundreds of geomodels that we want to take forward into simulation, generate the first Latin hypercube, and start the differential evolution cycle. Until we are happy with that, and then we select the final ensemble that we want to take forward into forecasting for our development concept options, and we run the economics, and when we feed in codec within values that we need for decision making. On the machine learning side, we start exactly the same in codec. The geoscientists preparing the geomodels, the RE preparing the base case, but then we go straight ahead into Azure, creating our first Latin hypercube, doing all the simulation runs, and then we take out the data for the data analysis to be done in our workstations. Once we have done all the learning, we take the output from it. And then the difference here is that we are optimizing not only the dynamic parameters, but we're also optimizing the geological parameters. So we're generating new geomodels based on the learning. And we are, as I said, constraining the dynamic parameters. And then we create a manual sampling with this output from the learning. We select our history match ensemble, and we do the forecast and go into economics and codec as before. During this year of cloud computing, we have done more than 25,000 simulation runs. Most of our fields are mature oil fields with extensive water flooring history. And we are the advanced recovery methods group. We are mostly working on chemical EOR, simulating polymer and alkali polymer flooring. In this year, we have completed these 6 projects where we have very large fields, field scale models, when we are talking about 5 million cells, 60 years of production history, and in the order of hundreds or thousands of wells. But we have also used the solution for sector models when we are working on pilot designs. And we're talking about smaller grids in the order of 500,000 cells or 1 million cells. Again, the same 70 years of history, because all of our fields are very mature, and less than 100 wells. And what we have seen is that the solution is good for different scales because it's adaptable and flexible. So what we have gained, right now we have access to 3,500 cores. We can select between a diversity of machines from 60 to 60 cores with different sorts of processors like AMD and Intel. And this has given us many possibilities. So right now, for example, we can select which system to use based on the throughput and the cost estimation. And projects have we have speed up projects by removing the blockage on having so limited availability of nodes and licenses. Our machine learning workflow has been possible due to this super computing power capacity, and we have other things that we really like on the system. One of them is that we are in charge of the data transfer, so the user is controlling how data is moving from one system to the other, and it's all done via the Geocloud. And we also have a user guide that for first-time users, which goes from how to log in the first time, how to authenticate, or how to change your password in the VDI. And it's something very useful to have. The things that we want to improve for the future, we want to work on bigger models with smaller cells. So we're talking about 30 million grid cells because we want to go down to cells of 5 meters. But right now we are already seeing that we need to exponentially increase our storage capacity because both workflows generate a large amount of data. We would also like to reduce the amount of data transfer and to improve the accessibility to the data we generate. And for this, we're thinking that a common data lake would be the most suitable solution. As we generate such amount of data, we need more efficient plotting capabilities. And on the methodology, we are working now on smoother the transition between forecasting and economics. And this is what I had to share today. Thank you very much for your attention.
Joanne, can you tell me if everybody can see the screen?
Yeah, perfect.
Wonderful. So good morning also from my side from Vienna. My name is Wolfram Questions, and I will give a little bit of insight on the project and IT point of view. Starting with the requirements and also give you some lessons learned which we took away from this cloud project. So as Giselle already mentioned, the benefit of this new stochastic workflow are really great, but also great are the computing power requirements. So we talk about 10 times more computing power this year and the next year and the year after as the demand for data and computational power grows and grows. We also require a very tight integration between the other platforms where the other colleagues are working, so to make sure that the collaboration between the other teams who prepare data, who get the feedback, is working well. We need the flexibility and a great user experience, meaning that our experts can spend their time working on the models and not required to wait for an IT expert to support them starting up a model or switching between different types of computing power. And last but not least, OMV is working and running projects globally, so we need to make sure that the solution which we build is global available and have a solid foundation with state-of-the-art security to protect our data and our user and our work. So how did we do that? It was very clear from the beginning that the existing HPC on-premise was not an option to expand. We had only limited possibilities to change our technical features. Every time we would invest in new hardware, that's when the point where we can choose if we want to go for a different GPU or a different CPU setup or switch to a new storage system. So also the multiple yearly increases would be very hard to organize and set up in our CapEx investments. So what we did is in early 2019, we did a proof of concept together with Cegal to validate our core requirements and made sure that these were met. And in summer, then we started with setting up an agile project together with Cegal and Rockflow Dynamics to implement coming from our POC to a full-fledged solution for our engineers to work. So using an agile approach also for a more infrastructure-related project was the idea to make sure that we start from clearly defined requirements with priorities and clear defined acceptance criteria. What makes sure that this is accepted, we can do it, and then go to the next step. And thereby we iterate, had very close feedback loops from the users testing a certain feature. Is the speed good? Can we scale to 10 nodes? Can we scale to 100 nodes? And then go from there. Once we were happy with the overall service and the stability of the solution, we handed it over to a service. We call it an evergreen service, as it will continue to evolve, where we can benefit from the continuous innovations from our partners, new infrastructure improvements coming in from Microsoft Azure, new cores, new GPUs, new features from RFD, or new enhancements in the overall solution and reports from Cegal. So when we talk about cloud, everybody says, okay, and agility, what are really the benefits? And I want to take you to one situation where we actually saw the huge opportunity by combining both agile and cloud to create more value for us at OMV. For one example is to find the sweet spot of performance. During the tests and the setup, we saw that the solution is very fast with our small models, but loading the results of our big models was considerably slower than the users expected. So we needed to improve that. The first analysis on issues and bottlenecks didn't prove any result. So what we did is we sat down and looked at what are the options, what are the potential bottlenecks, and what are the potential improvements which we can do, and sorted them by running costs. And then we reviewed our existing test scenarios and sat down and wrote the minimum expected criteria to make sure that the speed this is the speed which we need to achieve in order to accept the solutions. And then we started and implement the developed options one by one, starting with the cheapest option. And this gave us, once this was implemented, it was working, we went directly to a user feedback session where we could see if this is a speed increase which the user can accept. And once we reached that speed which we defined already before and is actually validated by the end users, we stopped and didn't need to continue anymore. So quite a difference to how you would work on improving when you have a physical setup or different solutions. So to have a look, what we have, the bottlenecks could be in Azure configuration, on the client, in the network, on the server side. In our case, we found out that the final speed increase which we actually needed was to exchange the file server, which we set up from Azure, to exchange it with one with higher specs, with burst cache, to make sure that the loading of the model is fast enough. So we didn't need to go to change for a very expensive storage option or completely review our configuration or do tests on the client. And this was then good enough. And also this will be the approach to enhance further computing requirements in terms of storage or simulation power. So how does the solution look like from a high level point of view? The user with his devices can choose directly to work in Geocloud, where he would be able to collaborate, have access to a lot more applications, and make sure that he can work. Or he would, if it's a more advanced project, he would work directly in the HPC infrastructure in Azure, and then have direct access to, at the moment, up to 150 computing nodes in parallel, either using pure CPU or a mixed version of GPU and CPU. The user, as Gisela already explained, has the possibility to personally control and bring the data up, run the simulation, and bring the results back to his environment without any technical interference and no support from a technical expert. Or he would be able to run the solution directly in Azure, run the simulation, monitor if the progress is good, and when he's finished, he could retrieve the results and continue working. So our takeaways from the first big cloud project are 5 takeaways I would like to share with you. Number 1, cloud solutions sound simple, also due to marketing, but they can get quite tricky. Make sure that you have the right experts on your team, from A to Azure to X like Express Route. Without the experts, you will not be fast enough and not get the right solution. Number 2 is, as I emphasized already, use agile methodologies to leverage the cloud capabilities and create value for you faster. If you are not so familiar with agile methodologies, there's tons of trainings out there to start or to get an expert. And I'm sure in your company there's already cloud and agile methodologies in place. Get in touch with them how to use that. Be flexible, but be concise. So know what you want to achieve, know your requirements, but be flexible on how to achieve them. Cloud is not fixed blocks, it's agile, it's flexible. There might be an opportunity to do a shortcut, and also a simple idea which you created at the beginning doesn't work as previously intended. So make sure you be flexible how you want to achieve your results. Invest in trainings for everyone. Cloud solutions are still new, and the technology to deploy them also as well. So everybody from the project also all the way to the service need to learn these new things. It's not native, it's not easy, and make sure that everybody has the right understanding how the thing is working to achieve also non-value during the project, but also in the whole life cycle. And last but not least, work tightly together with your end customers. Make sure you get really often feedback, and then come back to the technical team, improve and continue to make sure that you stay on the right track. Thanks everyone. Thanks for listening. Happy to answer your questions.
Thank you, Wolfram. Handing over to Marty.
It is quite amazing, isn't it? You can be home in your own house, drinking a cup of coffee, and then you remember you should have started that simulation job. You walk over to your computer and you basically click next, 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 and then hundreds or thousands of machines in a mountain somewhere is starting up and performing your job. When they are finished, they are all shut down and deleted. My name is Marty, and I'm a product manager from Cegal. Cegal is a trusted global digitalization partner for oil and gas, renewables, and ocean industries. We were founded back in 2000 as a generic IT company. In 2010, we started focusing on oil and gas specifically. And today, we have 13,500 end users. We support more than 1,300 applications, and we have 130 plus oil and gas customers. In 2019, we had a turnaround of $91 million. What is different about us compared to a generic IT vendor is that we also have hired in-house geologists, geophysicists, reservoir engineers, and experts in the industry, which means we understand what you need. Our products are built around our Geocloud model. It is where we take care of all of the integration work. We deploy the software, we configure your clusters, we deploy this in Azure, and then we operate, analyze, and optimize the product, where we go in an iterative cycle and then improve on the product over time. We believe this frees you to focus on your core business. Cegal has been hosting and operating HPC solutions for more than 10 years, but it's mostly been on premises. When the cloud started to make its tremendous impact, we knew that HPC would be a perfect candidate for this burst and peaky type of workloads. But we needed to partner with a visionary customer who had the in-depth insights to steer such an undertaking in the right direction. In 2018, OMV contacted Cegal with just such an opportunity. As part of the branch office of the Future program, OMV was investigating different approaches to reservoir engineering. They compared simulators, on-premises versus cloud solutions, and so on. With OMV at the helm and steering this initiative, together with Rockflow Dynamics and Microsoft, Cegal provided the expertise to build such a solution. In early 2019, we together created the very first proof of concept of this HPC solution in Azure. In the months and summer of 2019, OMV decided, on the basis of the proof of concept, that their strategic direction was an Azure-hosted solution using Rockflow Dynamics tNavigator and with Cegal as the integrator. Together, we started work in the end of 2019 to create what is now the final product and which is used in daily work at OMV. What we created is nothing short of amazing. With OMV's clear vision and requirements, Microsoft's unlimited potential of resources, and the excellency of Rockflow Dynamics software, we created the next generation of reservoir engineering. On the left-hand side on this screenshot, you will see the Geocloud Petrotechnical high-end desktop. This is fully integrated with tNavigator, which is delivered by our automated application pipeline. This again is wired together with our Geocloud portal. The portal is Cegal's one-stop shop for cloud products. In the Geocloud portal, you can access reports, do user administration, check your cluster overview, and other functionality that you won't find anywhere else. And in the end, the Geocloud portal is also tightly integrated with Microsoft Azure for a fully seamless working environment for the reservoir engineer. So what does that look like? It actually looks just like it did before. And that's a good thing, because you don't need any new training or any changes in how you work. But you now have access to the scalability of the cloud. The desktop is just as before, but it's in Azure. You have high performance storage, but this is also in Azure. And finally, your application is hooked up to the HPC resources of Azure, which gives you unparalleled agility, performance, and scalability. As part of all the work we did together, we also built some specific functionality around the HPC product. We created in the Geocloud portal a cluster dashboard. Here you can go in and get full control over your cluster. You can see all of the jobs that are running, the queues, the past history, how long they've been running for, and so on. We also created together a live cost report. It's very important to stay in control of the spending in Azure. So in here, you can see the cost on a job level, which is different than if you just set this up out of the box, because then you see the cost on a machine level. But here you see it down to the job level. You can see it cost per user, per queue, and also the total. And additionally, it's important to be able to group this cost towards the project that are doing the work, because then you can take that cost and charge it back internally, which helps a lot on the IT budget. And of course, there is a cost export. In here, you get access to all of the information around the jobs, how long they've been running, the cores used, the users, and so on, so that you can do post-processing. For instance, if you want to import this into SAP or another tool. Around the solution, it's also important to always stay in control. So we have created 3 different monitors that continuously checks and sees that everything is within the boundaries that you define. It's a safety net around the solution. The first monitor is a cost monitor. In here, you can configure a threshold. So say you only want to spend maybe €1,000 in a day. And if you spend more than €1,000 in a day, you want to receive an SMS or an email or both. This can be sent to specific users, which is by you configurable, so that it's just the right ones that should receive these alerts. The second monitor is the discount monitor. And this one I'm particularly proud of, because what we do here is that we scan the Microsoft price book regularly, and we look for a discounted version of the exact same machine you have today. Sometimes Microsoft will publish these machines, and then we pick up on that, and we use the same functionality where we can alert you via SMS or email. And then you can order this machine directly from the Geocloud portal. So you don't have to pick up a phone and call us or send an email. You just do it directly from here. This can save you upwards of 30% when you use these discounted machines. If you didn't have this, this would be a manual job. And finally, we also have now created a job monitor. This one makes sure that the jobs you expect to run for maybe 24 hours or 48 hours, that you can receive an alert if they use more than that time. And it's the same as the other ones. You can send SMS, email, and so on. And this allows you to take action. And what I'm showing you here is not available off the shelf. So in summary, this is a ready-made turnkey Azure solution. It gives the reservoir engineer access to unlimited computing power, which again drastically shortens simulation time. It's made specifically for the oil and gas industry. As I alluded to, we have in-house competence around this, so we can create it that it solves your problems as good as possible. It's made around a pay-as-you-go model. So there is low upfront investments, and the cost is associated with the usage. As far as we know, this is the only HPC product out there that is one platform with multiple simulators from multiple vendors. And of course, it easily scales to any size. As I've shown you, the live dashboard has a job overview. We have created a cost report with tagging support on project level. Over time, Cegal has acquired knowledge about which hardware works for specific types of jobs. So we choose, like in the Microsoft Azure environment, there are hundreds of different machines. But we know now which ones work best with which situations. And finally, when you use a solution like Azure, the hardware is continuously updated. This is quite different than when you're in your own data center, where you might be on a 5-year cycle, right? In Azure, I think there's maybe 2 or 3 different machines published each year that you can start using, and it's always state of the art and tuned for these type of workloads. In the end, it's all about the business impact. And with this solution, OMV was able to make better decisions with higher resolution models. I hear it's now practical and feasible to work with 5 by 5 meter cell sizes. In only 5 days, they simulated 2,000 simulation cases with nearly 70 years of production history. Of course, you no longer have to wait for available computation power. And this one I particularly like. It's when you're already in Azure, you're close to all of the innovation that's just happening right around you. It's not the same as when you're in a data center, because here you can start adding on other services, maybe not from Cegal, from another third party, but it's right next door to you, right? So you can start adding machine learning, other tools and so on, because you're already there with your data. And as you saw from Gisela, we are now doing machine learning on top of the reservoir simulation. And finally, this is a good one. The subsurface study was reduced from 12 months to just 3 months, which is quite the achievement. If you want to have the same solution that OMV has, please contact me directly or go to cegal.com. You navigate to Cloud and Geocloud HPC on Azure, where you can read more information and contact us. So thank you so much for your attention, and please take care of yourself and your family in these trying times. Thank you.
Thank you, Marcus. So now we just have a little bit of time left at the end for the Q&A session. So there have been some questions coming in from the audience, which I have shared with our speakers. I think we'll start with a question for Gisela. If you're ready, Gisela, I'm going to read it out to you. At the end, your workflow delivered a wide range of possible production profiles, which could be imagined without any calculation at all, such as taking the range from analogy. What do you think is the most benefit for doing all of these intensive computing operations?
Hi. So as I said at the beginning, the whole point is to do uncertainty management. If you just work with analogies or analogs, you are not using the information you have gained from the field, which is the historical data, and you are just, like, for example, saying, I'm going to take the umbrella today because it rained yesterday. This is your decision criteria. So it all depends how you want to address when you have to make a decision. In our case, we want to have a robust probabilistic model, so we make better decisions. And the only way to do that is to have an ensemble of history matched models. So it's not just one model, it's an ensemble, and we want the ensemble to be big and large enough so it has statistical meaning. And then I think you were talking about the spread of the example that I was showing on the incremental oil. This is combining different methods. This is combining the NFA with the water flooding with polymer or alkali polymer. If you look at each individual concept option, the spread is not so wide, but we want it to be wide anyway. So it is. It has a probabilistic meaning.
Thank you. We'll move on to a couple of questions for Wolfram. We have a couple of questions about CPUs and GPUs on HPC, so I'll just read them both. Maybe you can answer them at the same time. The first question is, how many CPUs are there on each HPC node? And we're also asked, are GPUs available for reservoir simulation?
Okay, yeah, thanks, Joanne. So the questions of how do we set it up? So as Marty's already explained in this presentation, we looked at different options, and right now we are having 4 different queues available. One is using GPU, and 3 are using different sizes and different CPU models. This is one with 16 core, one with 44 cores, and one with AMD 200, not AMD 60 core EPYC. So we have at the model 3 CPUs and 1 GPU queue available for the users to choose what works best on the model.
Thank you. And let's have a question from Mattis as well. Mattis, if understood correctly, earlier it was mentioned that passwords needed to be managed for the Azure environment. Does this mean that the Azure HPC solution doesn't have a single sign-on available? Is it on a different domain to the end user?
Hello, and thank you for that question. That was very astutely observed, and you are correct. There is a mixed environment in the HPC solution between Windows and Linux. We are working to try to solve the single sign-on for this, because that's of course something OMV and other customer wants. But at the moment, it's a quite hard challenge to tackle actually. So it's something that's high on our priority, but at the moment, users are local to the solution. So Cegal manages that on behalf of the customer.
Thank you. Let's do one more question for Gisela. What analysis is done in Python on the, oh sorry, I keep losing. What analysis is done on Python on local desktop to refine history match in ML workflow? Is it similar to assisted history matching analysis to identify critical history match parameters?
Okay, so what we are doing is random forest regression. We can do it on Python or on R, and basically we are feeding in all the parameters which have uncertainty, which are the geological and the dynamic parameters, and we're using objective functions as measures of the error for each simulation run and a particular measurement in the field. And the whole point is that we are matching not just, for example, the field oil rate, but we're matching several measurements at the same time. I think the answer is we are doing a random forest regression.
Thank you. Let's do one more question for Wolfram as well. How could AI and deep learning further develop, change, and positively impact the current workflow?
Thanks, Jan. But I think it's actually Gisela, if you can take this question about how AI and deep learning could improve the workflow or further improve the workflow. I think this is something you can answer better.
Well, what we are doing is machine learning. How to improve the workflow? We are working on many different things, like we're controlling the parameter space, how parameters interact to each other. So there are many doors for optimization. And on the plotting part, for example, we are looking for solutions to handle larger amounts of resource or larger amounts of data. So this could be an opportunity also to do something on machine learning.
Thank you. Okay, let's have one more question for Mattis, and then we'll wrap up for today. Mattis, can anyone create a pay-as-you-go cluster on Cegal Azure HPC?
Come again, sorry, repeat it, please.
Can anyone create a pay-as-you-go cluster on Cegal Azure HPC?
I'm sorry, I didn't catch it. Can anyone
create a pay-as-you-go cluster on the Cegal Azure HPC?
Can anyone create a pay-as-you-go cluster? Of course, anyone can create it by themselves if that is the question. But if you want this solution, of course, you need to come to us. Was that the question?
Yeah, I think so. That's okay. I'm sure they can drop an email.
Maybe I can just elaborate a little bit. Matthias, I think you answered it perfectly. The solution described here between OMV, Cegal and tNavigator, it can be made available for anyone. I think it's just a case of come and talk to us and we'll be happy to share details. It's not a problem.
Thank you, Scott. Okay, I think we will wrap up for there. There are a few questions that we haven't answered, but we're running out of time, so we'll make sure we follow up with you if your question wasn't answered live. So thank you again to all of our presenters today, to Gisela, Wolfram and Matthias, and of course OMV and Cegal for participating. And we look forward to seeing everyone for more webinars in 2021. Thank you very much.
Thank you.
Thank you. Thank you. Bye-bye.